Hassler here. I'm going to talk through the lesson in 7.1 as well as the notes. So it says a sequence of starbursts is shown, and I can see that I have 4 figures. The first question says, describe what is changing from one figure to the next. So automatically my thought is, all right, I'm going to total up how many starbursts I have in each figure. So I have 3 starbursts in the first figure. I have 8 starbursts in the second figure. Let's see, 3 by 5, I have 15 starbursts in the next figure. Let's see, 4 by 6, so 24 starbursts in this last figure. And if I had to describe how it's changing, to me it looks like I have 1 column but 3 rows. Let's see, here I have 2 columns, but now I have 4 rows. I have 3 columns, and now I have 5 rows. So it looks to me like I'm adding 1 column and 1 row to each figure. Okay. But one of the other things that I notice is, I go from 3 to 8, and so I'm adding 5. And I go from 8 to 15, I'm adding 7. 15 to 24, I'm adding 9. Okay, well, it does not look like I'm adding the same amount each time, which again is another pattern that we like to look for. But let's see, something that I do notice is that the difference between those two numbers, 5 and 7, the difference between my change is 2. And the difference between this change is also 2. So that feels kind of like a pattern to me. So I'm going to comment like, yeah, I'm increasing my number of starbursts, but the change in starburst. So my change in starburst goes up by 2. So I think that that's something interesting and worth noticing, that I'm not changing by the same number each time, that green number of add 5, add 7, add 9. But the amount that I'm changing by, that is changing by 2 each time. So something I'm going to keep track of. All right, what would figure 5 look like? Can I determine the number of starbursts in figure 5 without counting them one by one? So I'm actually going to use this idea that we just talked about, right? If the change in my change is 2, that means that I would have to add 11 to 24 to get the next set of starbursts. So 24 plus 11 would be 35 starbursts, right? 24 plus 11 gives me 35. But something else that I noticed as I was drawing out in blue here, I noticed the figure number matches my number of columns. The figure number matches the number of columns. And I also noticed that my rows happen to be 2 more than my figure number, right? So in figure 1, I have 1 column and 3 rows. In figure 2, I have 2 columns and 4 rows. In figure 3, I have 3 columns and 5 rows. Figure 4 is 4 columns and 6 rows. So I'm going to guess that figure 5 has 5 columns and 7 rows, right? I'm adding a column and row each time. And so it's this idea that I could do 5 times 7, which is also 35. So it's kind of cool because I can get this answer of 35 going about it in 2 different ways. Okay, so we are going to go ahead and record this information that we have. We said that in figure 1, there were 3 starbursts. And in figure 2, there were 8 starbursts, and then 15 starbursts in figure 3, 24 in figure 4, 35 in figure 5. Now I got to think about what would be in figure 10. And this is where I'm going to use the idea of this 5 times 7, right? We said that in each of these figures, I could take my figure number, so I'll abbreviate figure number, and I can multiply that by 2 more than the figure number, right? So the figure number plus 2. And so here I would have 10 times 12, and that's going to give me 120. Okay, so I should have 120 starbursts. It says, is the number of starbursts increasing by the same amount every time? And that's what we talked about up above, where I had the green drawing, right? I'm showing that change in starburst in my green, and the answer was no. I actually want to show that change here in my table. Do that with me. I had a change of +5, and then I had a change of +7, and I had a change of +9, and then a change of +11. And so no. First we're adding 5, then we're adding 7, then we're adding 11, etc. So I am not changing by the same amount every time. Can the number of starbursts in each figure be described as an arithmetic sequence? All right, well, to be an arithmetic sequence, I have to be changing by the same number each time. And so arithmetic, no. Not adding or subtracting that same number each time. So it's not going to be arithmetic. Is it a geometric sequence? So geometric. No, geometric means that I'm multiplying by the same number each time. And there's not a number I'm multiplying 3 by to get 8 and then 8 by that same number to get 15. So we're going to say no. We're not multiplying by a same number to get the next number. Now, you do not have Part D on your packet. I added this in after working through a little more thoroughly, and I want to talk about the pattern that we do notice. The pattern that we do notice is that while the first change here is not the same each time, the second change is. The numbers that I'm changing by are increasing by 2. And so we call this the second difference. It's the second time that I'm looking through for a pattern. The second difference is constant. That is going to be a huge deal. So if I notice that I have a pattern that's not adding the same amount each time, but that pattern is changing by the same amount each time, this second round of patterns is the same, then this is called a second difference. And that second difference is going to lead us into a new type of function that we're going to be talking about. Before we talk about that new type of function, I want to go ahead and let f of n be a number of starbursts. So that means that this is f of n. In the nth figure, so this input here would be n, and I want an equation. So my equation is actually the one I already wrote up here, right? F of n is equal to the figure number, that will be n, times that figure number plus 2. I'm writing it in words because I feel like it makes sense to me in words. I'm going to take the figure number, like here is 1, and I'm going to multiply it by 2 more than that. I get 3. The figure number 2, I'm going to multiply it by 2 more than that, 8. But I got to turn this into n's. So f of n is really n, figure number, times n plus 2. And the last thing I'm going to talk about is remembering distributive property. Distributive property is when I take this term on the outside and I share it with each term on the inside. By sharing, I mean I multiply. So I'm going to multiply n times n. Now this is actually a review of the unit we just did. Technically, these n's have exponents of 1, so n times n is n squared. And then I have to take that outside n and share it or multiply it with that 2. And n times 2 is 2n, okay? And so this is going to be a big deal as well, the fact that I have this n squared. All right, so we've come up with a couple of new ideas, looking at a second difference, or that second pattern being the same. I have this n squared that is popping up, so let's talk about what all of this means. On the back, when we look at our quick notes, I'm going to define a new function type for you, and that new function type is a quadratic function with a Q, quadratic. So a quadratic function is in the form y equals x squared. So every function we've talked about this year so far is a linear function, just y equals x to the first. We don't even write to the first, okay? We're going to talk about a new function, a quadratic function, and this has an x squared. There are 3 ways I can identify a quadratic function. The first way is that a quadratic function has a constant second difference. When I say a second constant has a constant second difference, I'm talking about this relationship up here. Not the first check of patterns, but the second check of patterns happens to be the same. That's the second difference, and it was the same, plus 2 each time. If that happens, I know I'm dealing with a quadratic function. A quadratic function is the result of multiplying 2 linear functions together. So I'm going to say it's the product. When I say product, I mean multiply. The product of 2 linear functions. Now, I still have this up here, and this n is a linear function. It's of that form y equals mx plus b, and n plus 2 is a linear function, because again, it's in that form y equals mx plus b. A linear function is when that exponent on the variable is 1. We don't typically write it. And so if I'm multiplying 2 lines together, I get this x squared, this quadratic function. And the last thing that I can say about a quadratic function is that the largest degree, and when I say degree, remember from last unit, that means exponent. The largest exponent is 2. Right? There's that x squared. I have an exponent of 2. Okay, so with this information, your job is to give the Check Your Understanding a try, problems 1 and 2. Let me know what questions you have on determining if something is a quadratic function or not, and then try the practice.